Hey everybody, welcome back. Last time we kind of wrapped up isotropic modeling. I showed how to estimate the same model using 3 different R packages, and also showed how to triangulate what the likelihood-based model tells you and what you can see based on a variogram. If you have not had a chance to watch the last video, notice there wasn't a ton of views. If you have not had a chance to watch the last video, it's super important because it sort of brings together a lot of the things that we've learned. This class, I know, starts out with a lot of definitions, but then we are right at that cusp where we start to apply what we learned. And so it's super important for you to keep up. So if you have not watched the last video, please do, because we'll be using a lot of those same R packages and learning new things in terms of anisotropy. So to date, we've been working with isotropic models. Isotropic models say that the nature of spatial correlation does not vary in space, does not vary with direction. Anisotropy formally has several parts, but almost everyone concerns themselves with what is called geometric anisotropy. That is when the range varies with direction, but the partial sill and the nugget remain constant as direction changes. So what you're thinking is your circular correlation contours for any point, either your observed point or unobserved point, our circular correlation contours become elliptical correlation contours. Right? So circle to ellipse. The circle is isotropy. The ellipse is anisotropy. I know these things are tough to say, anisotropy. I had to practice. It's important to note that we're still working in a stationary world. So although we are allowing spatial correlation to depend on direction, we're estimating one prevailing direction across our entire region. That is the only way we can make it work. There is something called zonal anisotropy. That's when the range stays constant and the sill and nugget vary. And of course, you can think of a mix of the two. But typically what people think is when you fix one, you fix the other, so to speak. And again, it's the geometric anisotropy that appears most often in the literature. So how do we do it? How do we specify? There are lots of ways of specifying an ellipse. The way we do it here is to have interpretable parameters. So 2 matrices, 1 and 2. We have a rotation matrix with its own anisotropy angle. And you can see that angle appears inside of these sines and cosines. And the angle measures counterclockwise rotation. So you think this is 0 degrees, this is 90 degrees, and this is 180 degrees. And so theta is how far over we get counterclockwise. Now in this unit, we have to go all the way back and remember what these angles look like in terms of pi. So 0 is also 0 pi, but 90 degrees is pi over 2, right? And 180 degrees is pi. 0 is also 2 pi, for example. So when we're talking about angles, we have to be very comfortable converting between angle and radian, which is in terms of pi. All right, we also have what is called a scaling matrix that has the anisotropy ratio in it. And it is measuring how much bigger the major axis of our ellipse is than the minor axis. So if I take this as my angle, which I don't know, around 130 degrees maybe, right? Between 90 and maybe 120 degrees. If I take this as my angle, then the ratio measures how much bigger the major axis is versus the minor axis. So of course, the larger this number, the larger the lambda, the more elongation we have. in the direction of theta. So here's how it works. We take all intersite distances. Remember stationarity, all intersite distances. We apply this to all of our locations. We rotate them counterclockwise through the angle theta, and then we compress the distances by lambda. We compress distances by lambda to induce greater correlation. All right, why does that work? We compress distances by lambda induce greater correlation in that direction. Here's why it works. Think back to a spatial correlation function, whichever one is your favorite. This is the correlation on the y-axis. This is the distance on the x-axis. If we now compress the distances by lambda, when we move, we literally move points closer together. When we move points closer together, we increase the correlation between them. So anisotropy induces greater correlation in direction theta by compressing the distances between our observed locations in that direction. That is why it works. Up here is our good old Euclidean distance. If we now multiply our rotation matrix and our scaling matrix, and I frankly forget exactly what the notation is for each of these matrices, and quite frankly, it's not important to remember what the notation is for each one of these two matrices. Their product is sometimes called G. That's when we apply both the rotation and the scaling. And when we feed it inside of our Euclidean norm, we get distances in this form, which are no longer Euclidean distances, right? These are now rotated and scaled, compressed Euclidean distances, which comprise what are called Mahalanobis distances. When we take Euclidean distances and then we rotate and scale them, they comprise Mahalanobis distances. And I'm using H star to denote them. These distances simply get put into our usual correlation functions, which then make up the variance covariances of our multivariate normals, and likelihood-based estimation proceeds as we've shown about 2 videos ago. So there's a key question here. We will recover isotropy. So isotropy is a special case of anisotropy if lambda equals to 1. Isotropy is a special case of anisotropy where lambda is equal to 1. Then theta doesn't matter at all. Why? Well, a couple of ways of thinking about it. Remember, isotropic world is that of a circle. Lambda measures how much bigger the major axis is versus the minor axis. Of course, in a circle, all radii are identical. So any kind of major axis, minor axis, their ratio is going to be equal to 1. You take that circle, and now you rotate it any way you want. You still get the same exact circle back. So if your anisotropy ratio lambda is exactly 1, theta is not estimable. You can't estimate it because you get the same circle back no matter what you rotate that circle by. That is not the case if you have an ellipse. An ellipse, if we now rotate by 90 degrees counterclockwise, we get this kind of ellipse. But in an ellipse, lambda is not 1 because the major axis is bigger than the minor axis. So the farther away lambda is from 1, the more the angle starts to matter. The farther away lambda is from 1, the more the angle starts to matter. Let's try and visualize this some more. Here's a reminder, right? We rotate entire coordinate system, all interpoint distances by counterclockwise by theta, distances are compressed by lambda, and this induces greater spatial correlation in that direction. So here we're showing how data in the middle, right there, correlate with their surroundings. So these are 95% correlation contours. So look, lambda is 1.5. This means the major axis is 50% bigger than the minor axis. Okay, simple enough. In no way does this shape resemble a circle. It very much looks like an ellipse. Our angle, 0.8 pi in terms of degrees, right, is 0.8. It's basically 8/10 of 180 degrees, which is around 140 degrees, right? Because it's 8 times 18, maybe 146 or so degrees. So then if we take this ellipse and we unfurl it, and now we plot what the range looks like as a function of angle. So we basically trace as a function of angle what that range is like from 0 to 160 degrees. We get that plot. Very interesting. Look, we are saying that 0.8 pi is about 140 degrees. That is also where our correlation peaks, our range, peaks. There, and of course, at twice that, which is about 280 degrees. So the range in the direction of 140 degrees is about 50% bigger than our smallest range, which is just whatever the direction is that's perpendicular, right there. Which would be 180 degrees minus 140, which would be 40 degrees. Which corresponds, of course, to the spot on this graph. So, let me repeat. Lambda is 1.5, which means that the range in the direction of greatest spatial correlation is 50% bigger than the range in the direction of weakest spatial correlation. The direction of greatest spatial correlation we found to be 0.8 pi, which is about 140 degrees. This means necessarily that the direction of weakest spatial correlation is perpendicular to that, or about 40 degrees. And if we just take that ellipse and we unfurl it, we can easily pick out 140 degrees as direction of greatest range, the largest distance at which data are correlated, and smallest range, where data are less spatially correlated, more independent. Okay, let's move on to the second ellipse. A little faster now, right? Okay, so for that ellipse, we're holding lambda constant. Lambda is 1.5. So the major axis is still 50% bigger than the minor axis. The range in the direction of greatest spatial correlation is 50% more than the range in the direction of weakest spatial correlation. But our angle is now pi over 4. Pi over 4 is 45 degrees. And so we see that peak occurring at about 45 degrees. This now ellipse is rotated by counterclockwise by 45 degrees, and the distances are compressed in that direction by a factor of 1.5, which induces greater correlation. Induces greater correlation in that direction. The last two ellipses, the angles stay the same, but lambda changes. Lambda is now 4. So with these ellipses, the degree of anisotropy is stronger because in this case, in about the direction of 140 degrees, the range is 4 times bigger than in the direction of about 40 degrees. And so this, of course, you can pick out the peaks a lot easier. So, my understanding question: what would a plot of range versus angle look like under isotropy? If you assume that spatial correlation is isotropic, you're saying it does not depend on direction. So you probably got it before I have a chance to draw it, but it would look like a flat line. Pretend that line is flat. Let me try and redraw it. It would look like a flat line. And between these two sets of panels, it is definitely the top two that look a lot more flat than the bottom two. So you can intuitively imagine how easy it is to detect, right? How easy it is to detect an anisotropy ratio of 1.5 versus 4 from your data, right? 4 is easier to detect. Even though, if you think about it logically, if your range is 50% bigger in one direction and another, that might feel like a pretty significant departure from isotropy. But thinking about it in these terms, anisotropy starts to really matter when that lambda starts to approach something like 4 and not something like 1.5. Let's take a look at some realistic examples. So this is a figure out of an Environmetrics paper by Mark Risser and Kate Calder. So this is an example of how precipitation around 4 weather stations in Colorado correlates with their surroundings. Right? So red colors are correlations. This is just a 2-dimensional version of the spatial correlation function. Red colors are really strong correlations of like 0.8 or greater. Then the light blue colors are moderate correlations of 0.4 or greater. And then as we get out into the blue and the purple, there is some correlation that persists, but it's quite weak. Remember, effective range is when correlation diminishes to 0.05, or in the one package, it's like 0.14. Look at how far out we have to go in these data to get down to something like 0.1, 0.05. That is why effective range can be quite large, even though the area of really strong correlation is actually quite small. Okay. All 4 ellipses are the same. All 4 ellipses are equally elongated, and all 4 ellipses are equally rotated. What is the assumption responsible for each ellipse looking identical? Stationarity. Stationarity. The nature of spatial correlation depends on direction, not on location. If we allowed those ellipses to be different, so maybe the leftmost ellipse would be pointing in this direction, the rightmost ellipse would be pointing in that direction, that would be an example of non-stationarity. We're not talking about that right now. We're talking about stationarity. What are the approximate values for lambda and theta? Let's go theta first. We rotate everything counterclockwise by theta. So here's 0, here's 90. It's definitely greater than 90, but maybe not too much greater than 90. My guess, I don't know, 120 or so degrees. Lambda, I have no clue, right? Lambda is how much bigger the major axis is than the minor axis. But if we go back here, those ellipses look a lot more like this one than like this one. And so my best guess is that that lambda is around 1.5. Yes, we're about to estimate these, of course. But just based on looking at this, the major axis is about 50% bigger than the minor axis. All right, so we're about to use R to do this. And of course, there are software challenges that are bound. Different packages do anisotropy quite differently. GeoR, I believe, has the most clear treatment of anisotropy. It forces lambda to be greater than 1. So deviation from a circle. And so theta always picks out the direction of greater correlation. That is what we want. We like that. Geostatus P, you have to be careful about because it allows lambda to be negative. It allows lambda to be negative. And how can lambda be negative? Well, if I scroll up, or here, I'm just going to introduce an empty slide. And for some reason, I am struggling with that. Here is an empty slide. All right. So far, we've been talking about positive angles of rotation. So to where, suppose this is about 120 degrees. I'm specifically using radians and degrees because we have to start thinking about it, right? 0 degrees, 90 degrees, 180 degrees. So here I'm rotating things counterclockwise by 120. Notice this is identical to rotating by negative -60, right? Because of course pi is 180 degrees. So GeoR requires that lambdas are necessarily greater than 1 and thetas are going to be between 0 and pi. So then the theta will always pick out the greater elongation of our ellipses. Geostatus P allows for negative rotation. You have to be very, very careful. A lot of triangulation that I demonstrated in the previous video. And I will demonstrate that again here. All right. You guys can read this slide. This slide just says that, look, remember that G matrix, right? G matrix is the product of the rotation and scaling matrix. We then make our anisotropic distances, feed them into our correlation function, for example, exponential. And then our range parameter measures the shorter of the two ranges, right? So in the shorter direction, phi star measures how quickly correlation decays. And then this would be the effective range in that direction. And then in the direction of theta, you just simply take this value and multiply it by lambda. So in the direction of greater spatial correlation, we take this and we multiply it by lambda in direction theta. And then, in between is everything in between. We fit an ellipse. And you can trace that ellipse in a variety of different directions. And that would be your range in a variety of different directions. Okay, let's flip to R and I will go through an example of what these anisotropic models look like in R. So first things first, I'm going to get my data. And I've uploaded these data online. And the first thing we're going to do is experiment with the two anisotropy parameters, the anisotropy angle, counterclockwise rotation, and the anisotropy ratio. So what I do is I work with scaled coordinates. The first two columns of this data set, by the way, are longitude and latitude. But what I do is I center and scale them so that they fit on the same set of axes. If I didn't do that, I would multiply the interpoint distance by something like 2, and it would blow up, and it would be hard to see the effect of anisotropy. Here, I simply turn these into z-scores. It preserves our interpoint distances. It preserves the locations. It just changes the units from decimal degrees to centered and scaled, right? Centered and scaled decimal degrees. That's all it does. Okay, so this is a helper function inside of GOR, and we will start with an anisotropy angle of 0. We're not rotating anything, and an anisotropy ratio of 1. So we are not rotating and we're not compressing. So when I pull those coordinates through my helper function, this will produce an identical image. And there we are. There are the original locations of the Colorado weather stations that are recording precipitation. And here are the same locations rotated by an angle of 0 and stretched by 1. We did nothing to them. Okay, let me start the rotation. All right, a little bit at a time. Here is 0.15, 0.15. Yep, so there, I just induced counterclockwise rotation of 0.15 pi. I believe this is pi over 8. Oh no, pi over between 6 and 7. So if pi is 180, then 0.15 pi is 27 degrees. 27 degrees counterclockwise rotation. And for now, I'm not going to stretch it at all. By the way, notice that the interpoint distances don't change at all because we apply the same transformation to all the locations at once. And you can tell, for example, here is a set of 5 weather stations. Here is a set of 5 weather stations. Here is a cluster of weather stations in the mountains. And then you can see what that looks like when it has been rotated. Here is a cluster of the same 5 weather stations. Here is the same cluster of the same 5 weather stations. I just reduced the vertical extent of my plot to make sure that it looks like this unit is the same as this unit because it is, right? These are all both z-scores. So this unit and this unit are identical. All right, here is 60 degrees, 0.33 pi, which is a third of pi, which is 60 degrees. All right, there's 60 degrees. I, for one, always, I think, underestimate what 60 degrees looks like. If you showed me that rotated and stretched set of points, I would say it's about 45 degrees, but that is why we don't estimate with our eye. We estimate with our R. There, okay. Okay, so let me keep the angle constant and now change my anisotropy ratio. I will now start to induce greater squeezing together of the distances in the direction of 60 degrees. So here's 1, here's 1.5. Our intuition tells us to not expect a huge difference. Our intuition tells us to not expect a huge difference. We saw some. We saw some difference. It's not huge, right? Here was a lambda of 1.5. Here's a lambda of 1. 1.5, 1. It's visible, but not that big. Here's what 4.5 looks like. That's pretty major. That's pretty major, right? When we reduce the distances in the direction of 60 degrees, by 4.5, we induce 4.5 times greater correlation in that same direction. Okay? Let me put this back to 1. And now rotate it maybe further to 0.8 pi. So notice here are the, here are the patterns of locations, and now I've taken them and I've rotated them over, right? Here are the same patterns right over there. And now I can play around and compress the distances in that direction by 4. Okay. I have a tool called the variogram. Here's what the isotropic variogram looks like. And in fact, if I'm being precise, this is the residual variogram because my data come with covariates. We have a covariate for elevation, and it's the centered and scaled elevation. We have a covariate for slope. It's the east-west slope to pick up the difference between the western range and the eastern range, right? The eastern side of the mountains and the western side of the mountains. We know which way weather moves in the United States. Most weather in the US moves west to east. So this is technically on lines 31 through 33, a residual isotropic variogram, like you did in your homework. I can now plot this. And here is my residual variogram. Clear evidence of spatial correlation in the data, even after accounting for elevation and east-west slope. My nugget is approaching something like 0.04, 0.05. My total sill is just over 0.1 there. My partial sill is the difference between them. Looks like my range is somewhere between, I don't know, call it 1 decimal degree here. Remember my units are in decimal degrees. I could easily do this in meters as well, and we know how to do that. This is an isotropic variogram. This is a unit on anisotropy. I have something called the covariogram map. So I'm going to estimate my covariogram map. And we know when we do that, I'm actually going to reduce my cutoff distance a bit. Keep the covariates in there. Here is my residual covariogram map. So this is picking out this direction. Now, to be clear, this is the same data. So this is the residual covariogram map that corresponds to these estimated correlation ellipses. Residual covariogram map, correlation ellipses. Interesting, very interesting. Of course, the look of this covariogram map very much depends on my, my distances. So here I increased my cutoff distance. Here I will decrease my cutoff distance. And it changes whether we pick off something that is closer to 90 degrees or farther from 90 degrees. And of course, to show you guys, I picked the most compelling set of cutoffs and bins to show you that clear direction of greater spatial dependence between northwest and southeast, and a lower spatial dependence of between northeast and southwest. All that is exploratory. And all of this is done with residuals. We want to work with data. That's what likelihood models are for. I'm going to use GOR. As per last time, GOR requires its own data format where we input a data frame. We specify what are the columns that contain the coordinates, what are the columns that contain our measured outcome variable, and what are the columns that contain the covariates. We have 2 covariates. We have centered and scaled elevation, and we have centered and scaled slope. All right, here we go. I'm going to fit a isotropic model, just to review from last time. The only thing I'm doing differently is I'm using REML as opposed to ML because it will give me better estimates for the partial sill and nugget. All right, fit this. It will run for just a tiny bit. First things first. Notice it's a British person who wrote this package. This is Professor Diggle's work. So maximize the spell like this. It's a British package. But look, we have 7 parameters, and we compare it to a non-spatial model with 5 parameters. Can we count our 5 parameters? We have an intercept. We have our main effect of elevation. We have a main effect of slope. We have the interaction, right? We have an interaction. We have an interaction between elevation and slope. That's only 4. What's the 5th one? In a non-spatial model, you're also estimating the residual variance. What are the 7 in a spatial model, isotropic spatial model? Intercept, main effect, interaction. I need to come up with 3 more. I have the partial sill, the nugget, and the range parameter. I'm trying really hard not to flip you guys off. All right, now we know what these models are estimating. We can take just a quick peek at what the AICs are returning. So look at this difference in AIC. The spatial model is just blowing the non-spatial model out of the water. We are using the exponential correlation function. The effective range is 6 decimal degrees. The effective range is 6 decimal degrees. If we go back to this plot, remember I said the effective range where that correlation function drops down to 0.05 is like really, really far. This matches this image, right? For us to get into the deep blue out there, we need to get really far apart. The really, really strong correlation, call it within the yellow band there, that's a lot lower than the effective range. If you wanted to compute what that was, you can just take your exponential correlation function and set it equal to 0.6 instead of 0.05 and find that distance. Okay. There is my partial sill. There is my nugget of almost 0. Here are my estimated betas. We've seen this all before. Okay, here comes the new stuff. We have not seen this type of output before. We can compare what the mean component looks like. The mean component is our x beta, right? Versus our latent spatial effect versus our residuals, right? Here is our mean. Here are our latent spatial effects. Here are our residuals. I can plot all 3 next to one another. Okay, and here is a default plot. So when you're looking at plots like this, I want you to be very careful because I have latitudes and longitudes. I have latitudes on my y-axis and longitudes on my x-axis. They're both measured in decimal degrees. They both have the same units. So when you're comparing, make sure that you scale the actual images to get approximately, right? Look, this is 1 degree distance. It has to be about the same as this one. So I can sort of try and do that here. But it can be hard to do depending on what your data look like. A little more. All right. Now, this is 1 decimal degree, and this is 1 decimal degree. So I will deform it a little bit so we can see the labels. There we go. Here is what my mean function produces. My mean function consists of the intercept, main effect of elevation, main effect of slope, and then the interaction between elevation and slope. So really, really high up and at a really, really crazy slope. Here are the spatially correlated latent effects. The entirety of the class has been all about the middle panel. Think about that. All 6 weeks of the class has made it to where we can produce and maybe even interpret this middle panel. These are isotropic. They have an effective range of 6 decimal degrees, partial sill, nugget, all that. So look, what happens is, if we were to fit a regular non-spatial model, we would need to downgrade the precipitation in the middle portion of the state right there, right? The mean function produces a large value and the spatial effects downgrade that. But in turn, the spatial effects upgrade the amount of precip out here in the plains. This is the state of Colorado, right? So it's quite flat and low elevation out here in the northeast corner, but the spatial effects say not so fast. They still get quite a bit of precip. So the spatial effects upgrade the precip out here in the plains. Looks like they downgrade the precip over here in the central mountains. What's going on in the northern mountains? Well, the downgrading of precip is a lot lower, right? This color right here is more greenish and light bluish. So you can think that the mean function is doing a really good job at explaining the precipitation here in the northern mountains, but not the central mountains. We need those spatial effects to downgrade the precipitation to correctly explain precipitation in the central mountains. Where is the ski resort? Oh, here's Steamboat, guys, right there. See this orange area? There's the Steamboat. What do you think? What do you think happened first? Did they learn maybe that there is a cluster of high precip out there out there by Steamboat? I think so. I think that is why they put the ski resort there. That's my guess. That's my uneducated guess. Residuals. What are we looking for there? From the very first week of class, we're looking for white noise in the residuals. If I flip to my notes, this is actually from the paper, Rissa and Calder paper. We see that after they fit the elevation, the slope, and their interaction, there's still clustering in the residuals. These residuals in their top right panel do not resemble white noise. There's spatial clustering in these residuals. We hope that the residuals in our rightmost panel do resemble white noise. And we have hard evidence to this effect by comparing the AICs of the non-spatial model and the spatial model. And of course, the spatial model beats the non-spatial model handedly. All right, that's all isotropic. Let's do anisotropic. It works the same way except for these two lines, where now we say fixed psi A is the angle, fixed psi R is the ratio. We say false. We don't want to fix them anymore, we want to estimate them. Now we have to give good starting values. How do you provide good starting values for your anisotropy parameters? To give good starting values for your anisotropy parameters, we have to look at our covariogram map, right? The angle is the hardest one. The ratio, you can just start at something like a 2 or a 3, 1.5. You know what? It's pretty sensitive to the starting values as is. There's not a ton of data to estimate these parameters, unfortunately. But angle we can do pretty well, right? So here, as I'm looking at this covariogram map, I'll start it at something like 120 degrees. Go for something like that, you know? 0.75 pi, 135 degrees, maybe 120 degrees, around there. Psi r, I'm starting it at that lambda, I'm starting at about 2. I can start at 3 and see what happens, but let me run it like this first. All right, we'll run just a tiny bit longer. We're estimating 2 additional parameters, right? We estimate 5 parameters with a non-spatial model. We estimate 7 parameters with an isotropic model, and we estimate 9 parameters with the anisotropic model, because in addition to all the parameters estimated by the isotropic model, we also estimate the angle and the ratio. AIC, we can compare. Yes, this does beat the non-spatial model, but does it beat the spatial model, the isotropic model? Well, I can look at my AIC of my isotropic model, 6.45. I can look at the AIC of my anisotropic model, it's 5.5. It's pretty close. I can look at the BIC, and I'll describe those later in this unit. Looks like it returns NA, even though it's clearly right there. Let me print out. All right, so our anisotropic BIC is just under 35. If I look at my, now I'm having trouble with R. All right, so the other one was, the anisotropic BIC was 34.96. The isotropic BIC is 29. So actually the BIC, or the Schwartz information criteria, is directing us to pick the isotropic model over the anisotropic model. Interesting, very interesting. Let's look at the output of the anisotropic model. Here is the effective range in the shorter direction. If you remember, the isotropic effective range was just over 6 decimal degrees. Here is the estimated anisotropy ratio, 1.523. Interesting. If we compare it to these plots, 1.523 does not correspond to all that great of a spatial dependence. In fact, anisotropy, I'm sorry. In fact, what we just estimated is probably looking a whole lot like this, right? Angle of 155 degrees, or 2.7 radians, and lambda, the ratio of 1.55. We have ratio of 1.523, all right? Partial cell, nugget, range parameter transformed into an effective range. Here are all the betas. Okay, interesting. AIC is telling us that the models are very, very similar. The anisotropic model is a little bit better. The BIC is telling us the isotropic model is better. And our lambda estimate, we know that's the one that matters. We know that the closer lambda gets to 1, the less the angle matters. We know that lambda is 1.5, which we can see does not correspond to all that deformed ellipse. So I can actually compare. I can take a look at this 3-panel figure and then output this 3-panel figure separately for my isotropic and anisotropic model. And in theory, all three are different. But can I actually spot this difference? All right, let's see if I can. Again, take care to make sure that if you're looking for things, take care to make sure that, here is 1 decimal degree and here is 1 decimal degree. You would be hard pressed to find a difference between these latent spatial effects. Look at the residuals. We know that these actually, I didn't make a mistake. I didn't make a coding error. These are actually different residuals. Look at the color of these. Look at the color of these. Look at the range of these. Look at the range of these. These are, in fact, different models. But you couldn't tell based on the latent spatial effects. And anisotropy is all about the middle column. It has very minimal effect on the mean function. Beta hats are found through the GLS equation, so that anisotropic variance covariance matrix will influence the mean function. But everything we learned about rotation, scaling, all the interpretations, all that applies to the spatial effects, and we do not see a huge difference. That matches up to our lambda being estimated quite near 1. That matches up to the AICs being quite similar, and BIC actually helping us pick the isotropic model. All right. Let me go ahead to doing the same thing using a different R package. This is the geostatistical package. It requires a spatial point data frame. We still pick out where the coordinates are, and when we fit our model, anisotropic model, here is the isotropic model, right? So Niso equals false will give us the isotropic model. We're not going to fix the nugget. Now we're going to work with a make-turn correlation function, shape of a half. A make-turn correlation function with a shape of a half produces the exponential. Make-turn correlation function, shape of a half, produces the exponential. We're going to fix this shape parameter. So this, look at this, here is our mean function right here. Here's the grid to make those pretty plots. So this is the isotropic model. And iso equals false. Here's the isotropic model. It will take a few seconds or so while we get to look at each other. Okay. Remember that this range is the effective range of the make-turn with a shape of a half, where the effective range is found with a correlation of just around 0.1. That's why it's less than 6, which is what GOR was returning. Here is the anisotropic model. Anisotropic model, I give the same inputs except for aniso equals true. So now we'll fit the anisotropic model, the anisotropic twin of that model. We get to look at each other for a few seconds because this runs for just a little bit. We are inverting a dense matrix. I do like the fact that GOR tells us what all the things that we estimated were. The shape we did not estimate. The shape we assumed was fixed at 0.5 because that produces the exponential correlation function. Scroll up, here are my estimates. Here is the range in the effective range in the shorter direction. Here is my anisotropy ratio. This should look quite familiar, but look at my angle. Minus 25 degrees. Geostatus P says minus 25 degrees. Minus 25 degrees. Where is my empty? I will just draw here. So to bring this puppy home, to bring this lecture home, GOR says theta is 155 degrees and lambda is 1.5-ish. So GOR says we go from 0, we rotate, here is pi over 2 or 90 degrees. We rotate by 155 and then we orient our ellipses like this. That's GOR. Geostatus P says both great packages, by the way. Theta is minus 25, right? Minus 25 degrees. Lambda of ratio 1.52. Also 1.5. So Geostatus P says we start at 0, and then we rotate counterclockwise by minus 25 degrees. And you know what? You can see that that picks out. Right? If we rotate by minus 25, that is identical to rotating by 155. So actually the two packages are returning the same result in two different ways. What Geostatus P allows us to do, though, is visualize where our anisotropy helped us and how. Well, here I can print out the prediction errors, the anisotropic prediction errors, and the isotropic prediction errors. And if we look, you see really closely, those are circular correlation contours inside the prediction errors. And these are deformed by 1.5 in the longer direction and rotated counterclockwise by 155 or counterclockwise by minus 25. So you can see pretty easily the effect that anisotropy had on our prediction standard deviations. You need to look a little bit harder to see the effect of anisotropy on our predicted precip. But if you just look at what happened with the precipitation in the central mountains here, it has been sort of smeared in this direction, which again is 155 degrees or minus 25. All right, guys, thank you so much for your attention. This concludes our exploration of anisotropy. We'll continue next time. Thank you all so much. I hope you guys are safe. Bye.